So this assignment is related to astrophysics and cosmology. The first two questions I solved the previous session, starting with question 3. The energy source of a main sequence star is a fusion of a hydrogen to helium in the core. Scientists have been unable to develop this process to produce a viable source of energy on Earth. Like if we, because the nuclear fusion happened on the stars, but why we are not able to make a controlled fusion? Explain why fusion is a viable source of energy for a star, but yet had been yes, but has yet to be developed as a viable source of energy on Earth. And in your answer, you should refer the condition necessary for fusion to occur. So this is a very common question, and every time you will find like such question in the paper. So first thing, for a fusion to happen, it required a very high temperature because we have to overcome the electrostatic repulsion between the nucleus. So first thing, for fusion to happen or fusion to occur, very high temperature is needed. And what is the reason to have a very high temperature? To overcome the electrostatic attraction between the nucleus. That is one thing. Then other thing, what we need a high density is also required for a sustainable fusion, for more collagen, and stars have the ideal pace. So these stars have ideal place for fusion because high strong gravity and high temperature. But on Earth, the problem is like we don't have a material, or we don't have like we need a very strong magnetic field to confine the plasma. So on Earth, there are main thing is like the containment of the material, like how we contain this material in a space. To undergo a strong like material, we need a very strong magnetic field for them to fuse them. And if they reach, like if the plasma touch the container, it will lose energy to surrounding and it will stop instantly. So the confinement problem, that's a main problem, is a confinement, and then very strong magnetic field is needed for the confinement. And we need a very strong magnetic field to confine the plasma. And another thing, the material may also melt, the container, the material may also melt because of very high temperature or greater amount of energy release. So these are the problems which are restricting us to make a fusion reactor. In question 4, in 1967, Jocelyn Bell discovered the first radio pulsar, which she has, which he was a research student at the University of Cambridge. These astronomical objects emit pulse of radio waves at a regular interval. The graph shows the variation in intensity of a radio wave was received from a pulsar. So you can see the intensity is changing. Use the graph show that the frequency of a pulsar of a radio wave from the source is between 0.7 hertz to 0.8 hertz. So you have to use a graph for this. And first we work out the time period. You can take any number of the vibration because frequency is reciprocal of the time period. So from this graph, the time axis there, I can work out the time period by taking a number of vibration, because if taking one vibration, it won't be that accurate. As there are more vibrations, so we'll take, this will give us an average time. So in this duration, like if we take, say, this is representing, this we don't know, like if I consider this as one, this will be one vibration, like because from here to here, one vibration, two vibration, three, four, five, six, seven, eight, nine, and 10. So it's like 10 time vibration happen. And what is the time for these 10 vibrations? It was not starting. This is not one. This is between one and two. So I guess this is 1.5. So from 1.5 to 15, this one is 15. So 1.5 to 15, it means 13.5. So 13.5 is the time for 10 vibration. What is the time period? Time for one vibration. So 13.5 divided by 10, it will be 1.35 seconds. So 1.35 second is a time for one vibration. And after getting a time period, so frequency is reciprocal of time period, so 1.35. So when it will be about 0.75 hertz. Why did not take this one? Because this is not clear whether it was completing a vibration or it's a peak or no. That's why I did not take this part. I ignored and I took the peaks because it's easy to recognize the peaks. That's why we use the peaks here. So frequency is 0.75. The next, the pulsar frequency was thought to be too high to have been produced by anything as large as like star-like sun. Consider the sun to be rotating with the frequency of zero point 0.8 about its axis as shown. Calculate the speed of a point on the sun equator if it rotates at this frequency. Diameter of the sun is 1.4. So if we consider that this is the point where it was, so this diameter is given for the sun. So we'll take half of it to get the radius. And we want to calculate the speed of a point on this sun's equator if it rotates with a frequency of 0.8. Like if it is rotating at a frequency of 0.8 hertz, what speed it is rotating. So we have the formula V is equals to R omega. So, and we already worked out the simple formula V is equals to R omega, and omega is equals to 2 pi f. The value of omega is, because omega is like basically 2 pi divided by t, that I can also find, or time period is reciprocal of frequencies, omega is 2 pi f. So in place of omega, I can write 2 pi f. So V is equals to R times 2 pi f, where R is the radius, the diameter is given, so we divide by 2, we'll get the radius, and 2 pi is constant, and the frequency is given already in the question, which is 8. Here the frequency, 0.8, sorry, not 8, 0.8. So we will work out the speed at which it is rotating, the radius, which will be half of diameter, so it will be 1.4 into 10 to the power 9 divided by 2 times 2 times 3.14 times the frequency. So frequency is 0.8. So we multiply, we get a speed is about 3.52 into 10 to the power 9 meter per second, which is a very high speed. Exponent 8 is like speed of a light. Explain why the sun could not be rotated at this frequency. Why the sun cannot rotate at this frequency? As you can see, our previous answer was more than the speed of the light. So the main, like why realistic? Because we say that nothing can travel faster than speed of light. So this is unrealistic because this value is more than the speed of light, or it is greater than. 3 into 10 power 8, which is practically impossible. Like nothing is can travel more than faster or more than the speed of the light, faster than the speed of the light. The next question, the sun actually rotate with much smaller frequency than given in B. The maximum speed of a point on the sun at equator is 4 into 10 power 3 meter per second. The light emitted from a sun with a wavelength 5.9 is observed on the earth as a line in the sun's line spectrum. The wavelength of this line differs slightly from 5.9 exponent minus 7 when the light emitted from A or B is analyzed. Why? Look, what will happen? Why there will be a different, like as it is rotating, if I say this is point B, why the two wavelengths, like what we observe, might be different. Like the light which is emitted from a center of the sun is 5.9. Like the center of the sun is emitting out a wavelength which is 5.9 into 10 to the power minus 7 meter. But when we observe, the wavelength of a line of this line differs slightly from 5.9 exponent 7 when the light emitted from A or B is analyzed. Because when we analyze point A or B, the point A and B, like because it's spinning in its own axis, so as a result, like position of A will differ, position of the B will also differ, like they will change. So there will be a Doppler effect as the, like if a source move towards or away, there will be a Doppler effect. As A is moving, like for example, first it was emitting here, but as sun is spinning, the A is light emitted from here. It's so this point A, if we are observing from the Earth, it is moving away from us. So if it is moving away from us, it means the wavelength will be longer, which we receive, but the frequency will be short or lower frequency. And for B, it appeared that it moved closer to us, like with reference to the position with Earth. So the wavelength which we receive from B will be shorter and the frequency will be higher due to the Doppler shift. So 1 mark is for mentioning Doppler shift and 1 mark is for relating, like when we are observing. And it will be other way around, like if you are observing from here, like if we are on this side, like facing A, then frequency of A will decrease and wavelength increase. But if you are observing from this side, like Earth is here, then the frequency of B will decrease and wavelength will increase, and opposite for A. You just have to mention a reference. Is it clear, this one? Any doubt in this? Then calculate the difference between the wavelength of a line observed in a spectrum from A and the line observed. So difference between the wavelength. So we will work out the Doppler shift. Like we need, because like using a Doppler effect, we have the formula that according to Doppler, like the Doppler shift, Z is equals to change in wavelength over original wavelength, or Z is equals to V by C, where C is the speed of light, V is the speed at which the object is moving. So in place of Z, we can write V by C. So we can say V over C is equals to change in wavelength over original wavelength. V is the speed at which the sun is moving, spinning. In this one, yeah. So the maximum speed of a point on the sun equator is 4 into 10 to the power 3. So the speed of this point is 4 into 10 to the power 3. The speed of the light is 3 into 10 to the power 8. The change in wavelength we have to find. And the original wavelength which was emitted from the point was 5.9 exponent minus 7. So this will be 5.9 into 10 to the power minus 7. This is divided, other side will be multiplied, and we'll get the change in wavelength, which is about 1.57 into 10 to the power minus 11 meters. So that's a lambda, delta lambda means the change in wavelength, the difference in the wavelength. No, that is when we multiply, this will be 7.87, 7.87 into 10 to the power minus 12 meter. That's a change in wavelength or delta lambda. But in the question, we have to find the change in wavelength, the difference between A and B. So the change in wavelength for A, like one will increase, other will decrease. So the change is 7.8 into 10 to the power minus 12. So example, for A, as it is moving away, the wavelength will increase. So for A, it will be the change, because like how much is the difference for, the wavelength will increase for A and the other one will decrease. So what will be the total change between A and B? You can solve in this manner. Like the delta lambda is equals to here, original wavelength minus the new wavelength. And here the delta lambda is equals to original wavelength plus the new wavelength. Or like the change in the wavelength for this point is 7.8 into 10 to the power minus 12. Like the delta lambda for this point is 7.8 into 10 to the power minus 12 meter. And same thing, the change in wavelength for B, it is also 7.8, because they have the same Doppler shift. Only one, the wavelength increase, the other decrease. 7.8 into 10 to the power minus 8. The question was, how much is a change of wavelength between A and B? That's a question. Calculate difference between the wavelength of a line observed in a spectrum of from A and the line observed from spectrum of B. Like, so it will be twice of it, because it is originally it is 5.9 into 10 to the power minus 7, and this will be because A is moving away, so the change in wavelength, the difference will be 7.8 into 10 to the power minus 12. But for B, the wavelength emitted is 5.9 into 10 to the power minus 7, but due to the different, like the change happened, so the wavelength will decrease by 7.8 into 10 to the power minus 12. If we want to, so we'll get the wavelength for A and we'll get the wavelength for B, and just we subtract them to get the difference in the wavelength. So it will be actually twice of it, because like if I say wavelength of A and wavelength of B, and when I subtract to know how much difference is the wavelength between the point A and B. So lambda A minus lambda B, this was 5.9 into 10 to the power minus 7 plus 7.8 into 10 to the power minus 12. That is A, minus the B is 5.9 into 10 to the power minus 7 and minus 7.8 into 10 to the power minus 12. So when we simplify this, this minus will multiply this will become plus. So this minus will cancel, they will cancel it. So it will actually twice of 7.8 into 10 to the power minus 12. So twice of 7.8 into 10 to the power minus 12, that was 1.57 exponent minus 11. So that will be the change in the wavelength between A and B. So this was a question from Astrophysics and Cosmology, question 4.